Hi everyone, my name is Yu Zhao, and here is our oral presentation of our final project. So basically what we did for a final project was that we trained a Minesweeper agent in a supervised learning fashion with DNN. And I would like to briefly talk about why we choose such a topic for our final project. Um, first of all, for the first question, why using a DNN to solve a Minesweeper puzzle? Um, so for my Minesweeper game, all you need to do is that given a certain state, you need to predict what is the next move you or next grid you are gonna uncover, which has the lowest probability containing a mine. In order to fully estimate such a probability distribution, we need to solve a problem which belongs to a sharp P complete problem. And you can basically assume that a sharp P complete problem would have a greater time complexity comparing to NP hard problem. So it makes sense to use the DNN to approximately estimate such a probability. And it's definitely true that DNN has a relatively lower time complexity comparing to solve this Sharpie complete problem. And the second question is that why using supervised learning? Because if you think about when training any like game agent, you would definitely use some reinforcement learning techniques to train such a model. But we made this decision for a single observation. So for a Minesweeper game, an early local optimum would not lead to a bad state, which means two things. First, we only need to train a model that only needs to consider a given prediction of local optimum. And secondly, we don't really need to consider any of the value states as reference for our model. Additionally, supervised learning could provide a more stable loss decreasement, which we think, for all these reasons, supervised learning may fit to solve this Minesweeper puzzle. Alright, let's talk more about methodology. So first of all, we would like to look at this model architecture. It contains basically all the details of our model design. So it makes sense to use a convolutional layer as a basic block for our model because the Minesweeper board looks very much like image pixels. And we further use some popular techniques for our model, such as residual connection, batch normalization, and rectifier unit. And the model architecture will finally output a vector with the same dimension of the board size. Of course, we will take the argmax as the prediction that our model will make for the next action. All right, loss function. We use a cross-entropy target function as our loss function in the end of the day. But we, instead of using a one-hot vector as the label for the cross-entropy, we used a uniform distribution, which means we evenly distributed the probability for every single correct next action, which means that if you take that action, you will never uncover a mine for the Minesweeper game. And we collect that data from our the game board, of course, and we use that as the label for our cross entropy loss function. And in order to further evaluate the validity of our loss function, we use the accuracy per action, which means if the action is accurate, then this action will never lead you to uncover a mine. And next thing, actual feature encoding. We found there are two things that are very important for our model to know. First of all is as a global feature, the number of mines is very important for the model to make prediction. And second thing, for each grid, the number over there is very important. For example, if you have a 0 over there, then it basically means all the surrounding neighbors contain no mines and they are safe to click. They are absolutely to be guaranteed as a good move for next step. Data sets. So we designed the data sets with some variant number of the number of mines in order to let the model to be trained so that it knows how to use the global feature we just talked about in the last section. And we use a lot of different game initializations in order to not let the model simply remember what is the answer looks like for a given state. Alright, that's so much about methodology. So let's talk a little bit about our results. First of all, I would like to talk a little bit about this graph. This graph basically means, as you can see, the loss decreased very fast and very stably as the accuracy per action grows up very quickly, and it goes along with the decrease of the loss. So we think we have successfully make a loss function ourselves, and we think we can basically verify the validity of the loss function. And secondly, we have achieved a 62 winning rates over a 20,000 update iterations. Comparing to other supervised learning methods such as SVM, they only achieve 5% of winning rate after training. So we think our results shows that we have somehow success on solving this Minesweeper solver problem. Alright, for other challenges in reflection, we have posted a final reflection on the dev post. If you are interested, we have answered every single question have been asked in the final project. But we still want to say a little bit more about some feature work could be done in the report. So first of all, the state-of-art winning rate is about 90% winning rate for a 6x6 grid size in 6 mines. But they used 440,000 update iterations. And if we could lower the learning rate at certain epochs, then I think we can achieve an even more winning rate. So the first thing we basically want to do in the future is definitely to train our model to get a higher winning rate, as high as possible. And something else we could do is that we can try different Minesweeper game setups, so that we can verify that our model is stable and it doesn't affected by the game setups. Alright, here is basically everything about our final project, and thanks for listening. Bye bye.